Have you ever wondered if you could teach a computer to actually think? I don't mean just crunching numbers, but to really reason, like a detective, piecing together clues to solve a mystery. Well, that's exactly what we're going to do today. We're going to dive into a kind of AI where every single conclusion is clear, explainable, and provably correct.
Okay, so let's get right into it. To really get what a challenge this is, we need to start with a puzzle. For us, it might seem pretty straightforward, but for a machine, it's a whole different world. So, here's our setup. 3 simple facts from the world of Harry Potter. You and I can read this, connect the dots, and probably figure out the answer pretty quickly. But our mission here is to give an AI the exact tools it needs to solve this very same puzzle step by logical step. Now, to get a computer to reason, we can't just throw English at it. It's way too messy and ambiguous. We need a formal language, something with strict rules. And that language is called propositional logic. Think of it like a blueprint. It's built from simple symbols that stand for facts, and a few key connectors that link them all together. This makes sure the AI's reasoning has no wiggle room. It's something we can always follow and trust completely.
All right, the first tool in our AI's toolkit is the easiest one. Not. And yeah, it works exactly how it sounds. If the statement, "it's raining," is true, then not "it's raining" is of course false. It's just a simple inverter, a basic on-off switch. This little chart is called a truth table, and it's basically a cheat sheet for logic. It shows us every possible outcome, no guesswork needed. As you can see, if our original idea, which we'll call P, is true, then not P is false. And if P is false, not P flips to true. It's a perfect switcheroo every single time. Next up, we've got and. Now, this one's a tough customer. For a sentence like, "It's Tuesday and it is sunny," to be true, both of those parts have to be true. If it's Tuesday but it's cloudy, nope, the whole thing is false. It's an all or nothing deal.
And this truth table for and really makes it obvious. Just look at this. You've got 4 possible combinations for P and Q, right? But only that very top row, where P is true and Q is true, gives us a true result. Any trace of false in the inputs and the whole thing comes crashing down. It's a high bar to clear. Now, or, on the other hand, is way more relaxed. If I say, "Harry visited Hagrid or Dumbledore," that statement is true if he visited one or if he visited the other, or even if he visited both. And this is a really key point. In everyday conversation, or can sometimes mean one or the other but not both. In logic, it's always inclusive.
You can see that chill attitude right here in its truth table. I mean, look at how many true results we get. 3 out of 4 possibilities work. The only way an or statement can possibly fail is if both parts are false. As long as you've got at least one true in the mix, the whole thing is golden. Okay, get ready, because this next one, implication, is the absolute workhorse of logical reasoning. This is what lets us create if-then rules, which is huge. Think of it like making a promise. If I say, "If it rains, then I will bring an umbrella," I'm making a very specific promise about what happens only when it rains. Let's use that umbrella promise to break this down. That second row is the only time I've broken my promise. It's raining, P is true, but I didn't bring my umbrella, Q is false. So the whole implication is false, I lied. But now check out the bottom 2 rows. In these cases, it's not raining, P is false. Well, my promise was only about what happens if it rains. Since it didn't, it doesn't matter what I do with my umbrella. I haven't broken my promise either way. So in logic, if that first condition isn't met, the implication is considered true by default. Okay, so we have our building blocks, not, and, or, and the super important implication. We get the rules. But how do we actually hand this over to a machine? We've got to translate these ideas into a language it understands. So let's see what this actually looks like in some Python code. So here we go. Here's that first rule from our puzzle, just in plain old English. It's a classic if-then statement, which should be setting off some bells. And notice, the if part has a not tucked inside it. And there it is, the translation. It's almost a perfect mirror of the English sentence. If it did not rain becomes not rain. Then Harry visited Hagrid becomes the second part of our implication function. See? This is the beauty of a formal language. There's no ambiguity. What you see is what you get. All right, let's tackle the next clue. This one's a little trickier, right? It's got an or in it,
but also this but not both clause, which is really just a sneaky way of saying and not both.
And this is a fantastic example of how we can stack our tools together. The first part, or Hagrid Dumbledore, is easy. That handles the or. The second part, not and Hagrid Dumbledore, takes care of that but not both condition. And since both of those things have to be true at the same time, we just wrap the whole thing up in one big and. We're literally building the exact meaning of the sentence using our code. So we've got all our rules coded up. How does the AI actually use them to find the answer? Well, it uses a really powerful but simple algorithm called model checking. The best way to think about it is that the AI just plays out every single possibility. It imagines a world where it rains and Harry visits Hagrid. Then it checks, does this world break any of my rules? Then it imagines a world where it doesn't rain, and so on. It just throws away any world that contradicts the facts, and then it looks at what's left. So we bundle up all our rules into a knowledge base, and we ask our question, rain. The AI runs through all those possible worlds, crosses out the ones that don't work, and what it finds is that in every single valid world left over, it had to have been raining. It solved the puzzle. Okay, so that was a fun little puzzle, but the real magic of this whole approach is that it can scale up. Now that we have an AI that can think logically, let's really put it to the test. Let's unleash our AI detective on a much bigger, more famous mystery.
That's right, we're talking about the classic game of Clue. We've got our suspects, our rooms, and our potential murder weapons. Our AI's job is to use the exact same logical deduction we just learned to figure out the one and only correct solution to the mystery, based on the clues it gets.
We just start by teaching the AI the basic rules of the game. For example, the rule that the solution has to be one of these 3 characters? Well, that's a perfect job for a simple logical or statement. We're just telling the AI that one of these has to be true.
Now here's the cool part. As we play the game and get new clues, we just add them to the AI's knowledge base. So let's say an opponent shows you the Colonel Mustard card. You now know for a fact he's not the culprit. So we just add the fact not mustard to what the AI knows, and it can immediately start eliminating possibilities.
After we've fed the AI all the basic rules and every single clue we've gathered along the way, we just ask it to run that model checker again. It will sift through every single person, place, weapon combination, throw out any that contradict the facts it knows, and eventually, it's left with just one possible world. It has solved the crime. Miss Scarlet in the library with the knife.
You know, we started with a simple 3-sentence puzzle, and we ended up with a crime-solving AI, all built on just a handful of basic logical rules. It really makes you wonder, doesn't it? If we can do this for puzzles and games, what other complex fields, from diagnosing diseases to analyzing legal contracts, could be broken down into rules an AI can follow? The possibilities are pretty amazing to think about.